Hello everybody, welcome to our Fundamental Physics Laboratory from Physics Department, Faculty of Science and Technology, Universitas Airlangga in Surabaya, Indonesia. In these experiments, we will have some activities in measuring of the liquid viscosity such as methanol, water and oils, as well as the students will make some comparisons and in-depth evaluations among them so that the students will have a good understanding about viscosity as one of the important properties of liquid. Have fun with this video and enjoy our dry experiments using these materials. Then let's talk about the viscosity. What is viscosity? This question is often best answered by example. Imagine a styrofoam cup with a hole in the bottom. If I then pour honey into the cup, I will find that the cup drains very slowly. This is because honey's viscosity is larger compared to other liquids' viscosities. If I fill up the same cup with water, for example, then the cup will drain much more quickly. So viscosity is kind of a measure of a fluid's resistance to flow. It describes the internal frictions of the moving fluid. A fluid with large viscosity resists motions because its molecular makeup gives it a lot of internal frictions. A fluid with low viscosity flows quite easily because its molecular makeup results in very little frictions when it's in motions. While materials and tools that we are going to use in these experiments is, first one, for Stokes methods, we are going to use oil, water, methanol as the materials, and the big tall glass for oil containers. 2 rubber bands for measuring the positions A and B, balls bearing for spherical objects, as well as 2 synchronized stopwatch. Materials and tools for Oswald viscosimeter method. In this method, we are using methanol as the materials, rubber pump to suck the liquid through the fine hollow in viscosimeter, and then Oswald viscosimeter itself, and 2 synchronized stopwatches. For the basic concept, we're using the Oswald equations. Here we will have the pressure difference between 2 ends, as well as we have the currents, how fast the liquids will flow through the tube. So eta here is actually the viscosity of the liquid, L is the length of the tube, R is the diameter of the tube. So we will have all of these parameters and we will define the eta as the viscosity of the liquid we measure. However, in this experiment, we are not going to use the Oswald equations. The origin of Oswald equations here is a bit hard to be used because it's hard to measure the radius of the fine tube as well as the current flow of the liquid through the fine tubes. So instead, we are going to use the second equation here, which is eta equals to pi hja powered by 4 divided by 8lv rho times by t. So all of the parameters here are equally constants. So we will derive the third equation here to allow us to compare between 2 different liquids. The first liquid, we already know its viscosity, but the second we haven't known yet. So by doing this comparison, the third equation here, we are allowed to use, and we will determine the third equation, the second viscosity of the liquids. So by doing the comparison between these two, we are going to use the third equation. The eta x is the viscosity of the liquids, which is we are not known yet, and we will compare to the eta w, which is the viscosity of the liquid, which is already known. In this case, we are using water. That's why the index here we are using W. Means this is the eta for the water. And rho x dx is actually the density of the liquids which we are not known yet, and the times when they are going through the fine tubes. And rho w t w is actually the density of water and times when they are going through the fine tubes. So all of the parameters we are going to use, and we will determine eta x, or the viscosity of your liquid, which is you're not known yet. The next one is the basic concept for the Stokes frictions method to measure or determine the liquid viscosity. In these techniques, we are going to use the object in the shapes of spherical, which is a ball bearings object. So when the object's going to free fall in the liquid, so that's actually there are two different forces applied into the object. The first one is the weight itself, which is the gravity, and the second one is the liquid friction, which is applied upwards to hold or restrict the motions. So in these situations, we are going to have the friction forces will be going increases and increases, and then once it comes to the equals, so the gravity will be equal to the friction force going upward. In this case, there is no accelerations anymore on that motions. It means that the object will be going downward without any accelerations. In these conditions, we are using that the equilibrium states can be defined using the following equations to determine the eta for parameter, which is your viscosity. So velocity here is the thermal velocity, which is the velocity of the object without any accelerations. Eta is the viscosity of your liquids, which is you need to determine, and rho is the density of the liquids, and rho dot here is the density of your object, which is your spherical ball bearing object. Alright, now we come to the experiments. How do we conduct or perform or carry out the experiments? For the Stokes method, the first one we need to do is we need to determine the density of the liquid using the liquid densitometer. So the liquid densitometer is kind of the object that can be floated on your liquid. So you just need to put it up into your liquid, and then the floating force will apply into the object. So you will know how far the object is going to sink into your liquid, and you just read through the scale on the object. So you will be able to determine the density of the liquid using this liquid densitometer. The second one, we need to determine the diameter of your ball bearing as an object. This ball bearing is a bit small, so you need to use the measure that's very proper in the rigors. So you need to take into account the least count of your measurements. So it's better if you are using kind of the screw micrometer gauge or vernier caliper to determine this diameter. I just want to remind you that in this case, we are going to measure the diameter of your ball bearing. You are not able to measure the radius, okay? So you're going to measure the diameter of your object. You can use either the vernier caliper or the screw micrometer gauge. The third one, we need to determine the distance between position A and B. This position A and B needs to be in the range of the motions while the object is already in the terminal velocity. So we will sign these two positions with the positions of rubber bands A and rubber band B. So you are going to measure the distance between these two. So you have an idea how far the distance between two positions A and B. Then the next one is we need to synchronize two timers or stopwatch. The purpose we are using this is we're supposed to have two synchronized timer because we are going to apply it at the same times, and then you will measure or you will record the times when the object travels from the rubber band A to the rubber band B. So with these two synchronized timer or stopwatch, you just switch it off when the object passes the rubber band A, and then you switch the other stopwatch while the object passes the position B. So by taking the difference between these two positions, you will know the times travels for the object travels from position A to position B. So as I said before, that the fifth one, you will allow to drop your object, which is ball bearing, from the surface of your liquid, and then the ball will go downward and passes A and B positions. In this case, you will be able to record the times traveling for the objects from A positions to B. Let's redetermine this viscosity of the liquid using the Oswald viscosimeter method. In these experiments, we will need to fill up the viscosimeter Oswald with the liquids. It should be in half of the viscosimeter volume capacity. So you will see the surface of your liquid hopefully at the half of your volumes, your viscosimeter volumes. Then connect the rubber bands to the viscosimeter. In this case, you are using Oswald viscosimeter, and it must be a little tube side. So there are two, like the Oswald viscosimeter is kind of the V shape, right? So you will have the left side and the other side of your tube, and the size are different. The one is larger than the other. So you're gonna use or apply your rubber pump into the little tube side one. All right. Then we need to synchronize two timers or stopwatch. It's quite similar as what you did in the first one, which is when you are using the Stokes frictions method. So synchronize the two timers or stopwatches and open the valve so the liquids will be going up and reach just above the position A. So you measured two different positions indicating by A and B, okay? And then release the rubber pump, then the liquids will drop and passes position A and B due to the gravity. So the liquids will be going through the wine tube and it reach A, then going past down to B because of the gravity. So what you need to do is you just need to record the time when the liquid meniscus on the fine, you can see on the fine tube, travels from A to B using the synchronized timer. Once again, you need to switch it off the timer A, and then you need to switch it off the second timer when it passes B. So you will take the difference between these two timers. Okay, so you determine the times traveling for the liquids from position A and position B. While you're measuring the distance between A and B, and you know the time traveling from A and B, from A to B, then you are able to determine the velocity. Okay, so you know the time, you know the velocity, you know the distance, then you're able to know the viscosity by using the third equations. With the third equations which I mentioned in the basic concept. Then we come up to the data. Your data is going to be filled up into these tables. You measure the temperature, you measure the density, you measure the diameter of your object, which is the ball bearing object, and then you measure the position A and B on the Oswald viscosimeter, as well as you measure the times traveling from A to B for different or various liquids you're using. Then you're ready for the calculation, right? The task. This is quite important for students to understand what they need to do and what they need to investigate, calculate, and evaluate. Okay? So students need to determine the viscosity of liquids such as water, oil, methanol, or alcohol. And then two methods will be used in these experiments by taking into account how viscous the liquids are. All right. So if you have the very thick liquid, which method are you going to use in this case? Or if you have not quite thick of the liquids, so which method you are going to use to determine its viscosity? Okay, so this kind of, you have a good understanding what is the difference between these two methods and why. All right. Then the second one, the student needs to compare between their calculations and their reference. And they need to evaluate whether their calculation is reasonably close or not by taking into account the error analysis from the error propagation they used. So this is quite normal that when we are doing the experiments and then we need to evaluate the error, so you need to use the error propagation on it, right? So by taking into account this error propagation, so you will be able to determine which one is pretty much closer to your reference, which one is a bit far compared to your reference. So you have an idea why this is very close, why this is very thorough techniques, while the other ones are not. So once you are already able to determine these two things, so you will be able to determine or to justify why we are using these methods and why we are using another ones. It depends on the thickness of your liquids. The more viscous the liquids, you need to use this method. The less viscous the liquids, you need to measure another technique. So this is the purpose you're using or you're doing these experiments.